The second control volume that looks somewhat different in this analysis with the regenerative feed water heating is the turbine. So let's analyze that. I'll draw a simple schematic of the turbine. And it's, in this example, slaved, connected to the second turbine as well by a common shaft. Okay, surprise, surprise, I will identify my control volume. And I'll also identify interactions between the system and the surroundings. Okay, the purpose of the turbine is to produce power output through work. So crossing the boundary, here's a rate of total work done by those two turbines connected together. Entering the turbine, I have state 1, mass flow rate at state 1. Exiting the first turbine, I have a portion of the fluid, M.2. And then exiting the second turbine, I have the rest of the fluid. That's M.3. Okay. Hopefully you can convince yourself that conservation of mass, it looks exactly the same. M.1 equals M.2 plus M.3. Let's move forward at this point. And we can use, again, you can reference the first law flow chart if you need to. Let's apply the first law on our control volume. Using the same assumptions as before, I end up with 0 equals. I do not have, well, I have heat transfer. It's negligible for a turbine. A turbine is a device that's intended to take fluid energy and produce work output on a shaft. So the important terms here, I've got the power being generated through work. I have energy being carried in by the fluid through enthalpy. I have energy leaving in 2 locations. Okay, let's do the same as we've been doing. Divide both sides by mass flow rate, or the total mass flow rate. I have to be careful here because not every component sees the same flow rate. Okay, and let's see here. Let's move the work term over. That'll become positive, and I will call that, that's my definition of specific work of the turbine. Notice that I'm dividing by the total mass flow rate. That's my reference point. And then on the right-hand side, let's, well, here, I'll just write it out. Okay, let's gather terms. H1 minus H2 plus 1 minus Y, H2 minus H3. I got that just by expanding terms and then collapsing them again. Okay, so this represents now the specific amount of work done by my turbine. Again, specific work based upon the total mass flow rate, M.1. Let's go ahead and look at the other components as well. The pumps look no different than before. I just have 2 of them. So I will I will declare that the work of the pumps, again, specific work based on the total mass flow rate, looks like the enthalpy at state 7 minus the enthalpy at state 6. That's the work done for pump 2. And then for pump 1, how did I get that 1 minus y term? Well, I applied the first law to the control volume of pump 1 and pump 2, and then I have to realize that pump 1 is seeing a reduced flow rate. It's seeing m.3. And then I divide everything by the total flow rate, m.1, and similar to the process shown above, twice now, I end up writing it in terms of the fraction y. Boiler. That looks the same as we've been seeing all along. And the condenser. Well, let's do this one with the first law. We'll have m.3 times H3 minus H4. Okay, again, I want to write this in terms of the total mass flow rate. So what I do is I divide both sides by the total mass flow rate. Algebraically, no problem with doing that. And then this becomes my definition specific heat transfer. And then here I have m.3 over m.1, which is my definition of 1 minus y. Okay, so I've written my first law for all of my different components, and we focused on the turbine and the open feed water heater because those look slightly different than what we've been seeing with the Rankine cycle. But I'm in a position now where I can calculate the total amount of work produced by the turbine. Remember, I have to subtract what I have to use to drive the pumps. And I have the heat transfer that's coming in through my boiler. So I could easily calculate my cycle efficiency. Thermal efficiency of my cycle. Again, that's going to look like what I want, which is my net work divided by what I have to pay for, which is my heat transfer in. In other words, the power produced by the turbine minus the power produced by consumed by the pumps divided by the power coming in through my boiler. And since I've written all of those previous terms based upon the same total mass flow rate of the cycle, I can write it in terms of the specific work and specific heat transfers. And just to make sure there's no confusion, again, it's understood that the power produced by the turbine is a positive number. The power it takes to drive the pump should be subtracted from that. So I might just put an absolute value sign around just to make sure we're completely on the same page.